Hi, we're doing Kinetics round 2 for you. So with Kinetics, we're going to keep going from where we were in the last one. Now our energy, remember we've got this potential energy diagram where it goes uphill and we can't do anything until we get to that very top. And once we get to the top, it will go down really quickly. Just like if you're riding your bike up a hill, it takes energy to get up the hill. And then when you're at the top, you don't have to pedal anymore once you get over that crest. Same thing here. So all reactions, even those that release energy, require energy to get started. That's that first going uphill. That's known as the activation energy. Now we also have high activation energies, low activation energies, regardless of what this graph looks like, this potential energy diagram. Activation energy is from your lowest starting point to the highest point. Now this first graph has a really high activation energy. The second graph, not as high, because we're starting in the middle and ending up high. So this activation energy is not as big, which means it might get going faster. Now this was where those rates of reaction come into play as well that we studied in the last, a week ago. So there's another thing that we can do for an potential energy diagram, an activation energy. We can reduce that activation energy using a catalyst. Now, one, the same information is still true for all the potential energy diagrams that you've already learned. It's all still true, okay? The thing is, activation energy is decreased. So here is our regular, this black line is our regular reaction. When we add a catalyst, all it does is the starting point is the same, the ending point is the same, this middle part is different. It reduces the activation energy. It reduces the amount of energy it takes to get going. So you don't have to bike up that hill quite as far. This is different. That is the only thing that the catalyst does. Now remember, a catalyst does not get used up during a reaction. Okay. This does not change. Our delta H does not change with a catalyst. Positive is still endothermic, negative is still exothermic. Because our products and reactants have not moved, they have not changed. Okay, so spontaneous. There's that word spontaneous. We've talked about it in class. It's going to happen all on its own. Well, how does that happen? We have to get, up that hill. So spontaneous means once we're at the top, it's going to keep going all on its own. It's going to keep going and going and going, sort of like a nuclear reaction. It's going to keep going and going. It started, we're not stopping it. Other reactions that we've seen, baking soda and vinegar. Once we get it started, it keeps going until we run out of stuff and run out of all those reactants. Ideal conditions. We have to have a balance between enthalpy, that's our heat of reaction, and our entropy, that's our disorder. Next thing we're going to look at is the heating curve of water. And I have a little video for you to watch about this. But heating curve of water, we've got solid water here. And then we're going to melt. And then we're heating up this water. And then it boils or vaporizes. And then finally we've got gas. And we can keep heating that gas. Hard to do in a kitchen, hard to do in a lab, but it can be done. What we're going to focus on is where each point is. And I want to take a look at this middle part right here, because there's an equation you're going to use on table T. And we're going to focus on that center part, and it's called a heat calculation, heat calculations. Q equals mc delta T. Q is energy, so that's going to be in our kilojoules. How much energy does it actually take to heat up that water or whatever else, but we're primarily going to use water. M is mass, so we have to know the mass in grams. C is our specific heat capacity, and that's on table B. That's why we're focusing just on water. Specific heat capacity, table B, you use the number exactly as written. And then delta T. Delta means we're subtracting. Final minus initial. You do not need to convert your delta T. It does not have to be in Kelvin, does not have to be in Celsius. They both have to be the same. Don't subtract a Kelvin from a Celsius or a Celsius from a Kelvin. Both in Kelvin or both in Celsius. I want to go back one slide here. This is the heating curve. A cooling curve goes the other direction. We start with gas, and then we condense it, and then we cool down that water, then we freeze it, and then we have solid. So the only difference between a heating and a cooling curve is which direction we're going. Heating curve goes up, cooling curve goes down. Okay? So that is all you need to know for now. There are more videos on our quarter 4 materials if you want some more information.